This is the video lesson for Geometry, Section 2.1, Patterns and Inductive Reasoning. So inductive reasoning is reasoning based on patterns you observe, or it's basically an educated guess. And so let's look at some ways we can use inductive reasoning using a pattern. So here in our first example, we have some numbers, 3, 9, 27, 81, and we need to use inductive reasoning to figure out what the next two terms we would think would be. So we can see here the pattern looks like it is times 3, times 3, times 3. So an educated guess on this using inductive reasoning would be the next term would be 81 times 3, which is 243. And then the next term after that we would assume would be times 3 based on this pattern, 729. Okay, we can also use that if we notice patterns in figures. So here we have a circle, a triangle inscribed in a circle, and this is 3 sides. Now we have a square inscribed in a circle. This is 4 sides. And then we have a pentagon inscribed in a circle. This is 5 sides. So the next term we would use, our educated guess would be 6 sides, right? A hexagon. 1, 2, 3, 4, 5, 6. And then 7. Oh, 7's going to be hard. 1, 2, 3, 4, 5, 6. Okay, I didn't do it right, but you get the point. It should be all a perfect. All the sides should be even, right? All these sides are congruent and even, but 7's hard to do. Okay, and then here is one for you to try on your own. See if you can see a pattern, and then use your inductive reasoning to guess what the next two terms, or educated guess what the next two terms would be here and here in this picture. So press pause, try this on your own, and then check back for the solution. Okay, so it looks like this first one was just going down by 5 every time. So we would assume the next two would keep following the pattern, and we would have 25 and then 20. And then in this picture, we just have one square, or with no diamonds inside. Then we have 1 diamond. Then we have 2, a diamond and a square. So now we're going to do 3, 1, 2, 3, and then we're going to do 4, 1, 2, 3, 4, and so on like that. Okay, so that's patterns. So with patterns, right, it was easy for us to just continue the pattern for the next two. But if we want to find like the 10th or the 20th or the 100th term in a sequence rather than every previous term before it, right, we're not going to do this 100 times to figure out what the 100th term is, right? We can use the pattern to make a conjecture about the sequence, and then you can use that conjecture to figure out what that 100th or whatever term we're looking for. So a conjecture is a conclusion that you reach using inductive reasoning. And this is about a pattern. Okay, so here we're going to use inductive reasoning. So what conjecture can you make about the number of regions 20 diameters form? Okay, so here in this picture we have 1 diameter, and then this forms 2 regions. Right here we have 2 diameters, and we have 1, 2, 3, 4 regions. Here we have 1, 2, 3, oh, sorry. Oh, we can do it this way, 4, 5, 6. We have 6 regions, and this is 1, 2, 3 diameters. So if we can look and see what this pattern is between diameters and regions, this is 1 goes to 2, 2 becomes 4, and 3 becomes 6. So maybe you notice there's a pattern here, 1 times 2. 2 times 2, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. So the conjecture I can make is that the number of regions is 2 times the number of diameters. So if we have 20 diameters, then times 2 would be 40 regions. All right, see how that works? So here is an example for you to try. What conjecture can you make about the 21st term here? So it goes RWB, RWB. So you can see that pattern, but without writing out RWB 21st, it should have been 100 or something else that makes it so that you wouldn't write it out. But don't write it out. See if you can figure out what the pattern is, and if you can guess what the 21st term is based on your conjecture, based on this pattern. So press pause and then check back for the solution. Okay, so for here, I noticed, right, I just count, this is 1, 2, 3, 4, 5, 6. I noticed that B is, or 21st term, this is changing every 3. And so the multiples of 3 are falling on the B. And since 21 is a multiple of 3, that's going to be a B. Another way to do this in the homework too, this comes up in the homework, and it's not exactly a multiple. When you have a pattern that changes by 3s, right, you can just take that numbers term, so like 21, and divide it by that however many times the pattern is changing, and then use the remainder. So 3 goes into 21 7 times with a remainder of 0. And so the remainder of 0 is going to be that third term. And so it kind of goes like this. This would be all remainder of 1s would be R's, all remainder of 2 would be W, and then all remainder of 0 would be B. So then 1, 2, 0. So basically, if we wanted to do the 100th term, right, take 100, divide it by 3, and that goes in 3 times, 10 3 times, 9, and then we have a remainder of 1. So all the remainder of 1s are going to be R. So the 100th term would be R. So that's another way to do it. Okay, and then just a little note here. You must have enough data to make a conjecture, right? If we just had RW, right, you wouldn't know if even about the B, right? Or if I stopped here with RWB, you don't know if there's another color. So this is just showing you that the pattern is going to keep repeating. So you do need to have enough data to make a conjecture. So we're going to move on to a little bit more difficult ones. So collecting data to make conjectures. So this question is asking, what conjecture can you make about the sum of the first 30 even numbers? So we're going to want to make start just collecting data on the first, maybe we don't want to do the first 30 even numbers. Let's just start by the first even number, right? The first even number is 2, right? And the sum of that is just 2, right? And let's see, the second one, right, would be 4. 4 plus 2 is 6. 3 even numbers would be 12. 4 even numbers would be 20. Okay, and let's see, and this says sum of the first 30. So this is just 30 terms. So this is 1 term, this is 2 terms, this is 3 terms, this is 4 terms. So what we want to get is up to 30. So I'm not going to do this here 30 times, right? I want to see if I can notice a pattern between 1 and 2, 2 and 6, 3 and 12, 4 and 20. Okay, and something I do notice is this is 1, I know 4 times 5 is 20, and I know 3 times 4 is 12, 2 times 3 is 6, and then 2 times 1 is 2. So maybe that's what, so if we call this, so now with 30, right, we're going to be, this is 1 more than this number, 2, 3, 3, 4, 4, 5, so this should be 31. So we should be timesing by 31. So 30, my guess would be 30 times 31, which is 930. So see how I didn't have to do all of this stuff in between. I didn't have to then add 10. Although if we did that, look, it would work, right? 5, we're going to say times 6 is 30. Yeah, because we'd be adding 10 to this. So you can see that pattern still holds for 5. And if we wanted to go to 30, we would just add 1 to 30 and then multiply them together. Okay, so try one on your own for, so basically kind of do the same thing, but this is now for odd numbers. See if you can notice a pattern for the first 30 odd numbers. So do it the same way that I collected the data and see if you notice a pattern. So you can rewind the video and pause it when the other one's on the screen if you need help with that. But press pause, try this on your own, and then check back for the solution. Okay, and so for this one, with 1 term, you get 1. With 2 terms, you get 4. 3 terms, you get 9. 4 terms, you get 16. And then maybe this pattern was a little easier to notice than the other one, right? 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4. So the conjecture is that the sum of the number of odd numbers you have is just that number of odd numbers times itself. So for 30, it would be 30 times 30 is 900 based on that pattern. And just another note, you must test your conjecture multiple times. If you find one counterexample, then the conjecture is false, right? So we did this 4 times, right? And we could add another one, or maybe it was okay with just 3. But if you find one that doesn't work, that means it doesn't work at all. And so if the one that doesn't work is called a counterexample. So new vocabulary word, counterexample. It's an example that shows that a conjecture is false. So let's look at some examples of finding a counterexample. So what is a counterexample of each conjecture? So if the name of the month starts with a J, then it's a summer month. Well, that's true for June. That's true for July. But what about the best month of the year, because it's my birthday month? Just kidding, it's not the best month of the year. It is January, right? That is not a summer month. So this is my counterexample. And when it asks for a counterexample, you just have to write it, right? You can just write January. That's just showing that this is false, right? This can't be true because of January. Okay, and B, you can connect any 3 points to form a triangle. Well, here's 3 random, there's a triangle, right? That looks fine. But what about if we have 3 points on a line, right? That does not make a triangle. So here's my counterexample right here. And sometimes it can just be a picture. Look at these 3 points. Here's an example of 3 points that do not form a triangle. They are called collinear. Or you could just write 3 collinear lines. Either one, picture or words. Okay, and then another one, when you multiply a number by 2, the product is greater than the original number. So when you multiply a number by 2, let's pick a number. Well, let's pick 0. What happens? 0 is a number. What happens when we multiply 0 times 2? We get 0. Is this product greater than the original number? 0? Which is my original number? No, they're the same. So you don't even have to write this part. You can just show this right there. That is your counterexample. Okay. Do I have one for you to try on your own? I do. I actually have 3 for you to try on your own. So practice your counterexamples. If a flower is red, it's a rose. And then this one and then this one. So see if you can come up with 3 counterexamples for these 3 conjectures. Press pause, write them down, and then check back for the solutions. Okay, so these are just my counterexamples. You can have other ones. Yours don't have to be the same. But A just has to be any other flower that can be red. So I said tulips can be red. Any other flower that you know that can be red could also be a counterexample. B is probably the hardest one, right? Because this is all still kind of new, but that is one way to name, remember the definition of a plane is 3 non-collinear points. There's only one plane that goes through 3 non-collinear points, but there's excluding the word non-collinear here, which means you can have 3 collinear points and there's infinite amount of planes that go through them, right? If they're all on the same line, right, you can have a plane that goes this way, you can have a plane that goes that way, and they could all have that line on it. So that is an example of that's a counterexample that makes this false. And then here you could have picked any number that when you multiply by 3, you get something that's not divisible by 6. I picked 5. 5 times 3 is 15. 15 is not divisible by 6. So that is a counterexample for that conjecture. Okay, that's it. Enjoy.